Okay, explain the wave project assignment with the clarity of 5 a.m. So we're learning about water waves. The why, the fundamental unit underneath chemistry and underneath the atom and underneath the properties of matter, is this realm where things behave like waves. Right? So you can learn that mathematically, or you can learn it kinesthetically, visually. So we're just looking at waves, right? So I just want you to understand an ocean wave, which is kind of incomprehensible. I don't understand. No, like they're not very well understood. It's one of the least studied things around, is the anatomy and the mechanics of ocean waves. How they form, how they get so big, like what the pattern of energy is that moves through the water. Like, it's not very well known, but it's known. Like, you can sit there and look at it, and you can like ride it, you can surf it. And so that pattern of the wave, like the way that the medium lifts up away from something that it's attracted to, right? It lifts up into something else, like a wave. This wave that we're looking at lifts up from a medium, the water, and it has to be on a surface. And so the surface is what? It's that medium plus something else, of like a lighter density, of a more rarefied density, the air. So water and oil can create waves on their surface, right? So you need a bottom or a center, something like that, and then this layer that creates the surface. That's the surface of the ocean, right? So there's all these parts of a wave. An electromagnetic wave is like what we're trying to figure out, but also like electrons. Electrons are entirely wave-like. And so when we're talking about chemistry, or when we're talking about electricity, or when we're talking about light, we're talking about these electrons. You know, they say they're sharing photons, et cetera, et cetera. But they have wave functions that look like the same way that water behaves under certain conditions. And so you can understand why the electromagnetic field is behaving that way. And then you can also see what the electromagnetic field is. Maybe not instantly, but the only way to get this picture is by studying a wave that you can see, a wave that you can study, a wave that you can understand. So I've been showing you videos. I've been showing you different ideas and concepts about waves. Trying to have conversations, and then also drawing basically just anatomical diagrams of waves. Right? So those anatomical diagrams mean that you're looking at the anatomy, you're looking at the parts of a wave. What are the parts? Okay, the water, that's a part. Then there's the energy moving through the water. That's definitely a part. That could be seen as more of the wave than the water, because it's just moving through the water. So it's like, where's that energy? It's invisible. Okay, so how do I represent that? And where is it in the water column? Where is it in the medium? And then what is that medium made of? Well, it's made of like the medium itself, and then the medium has a surface. And then that surface has to be arranged in some sort of other field such that it stacks and it has density, right? Like within a gravitational field, rock or sand has more density than water, has more density than air. So there's some arrangement where there's three different mediums: a ground, and then the medium or the field, and then the air, or some lighter substance, some more rarefied thing. And then when you have that set up, that's like the anatomy of a wave. So then what does that do? So as the wave goes by, the surface goes up. The surface wants to be level, it wants to be neutral. So you could have a nice calm lake and you throw a rock in it, and that rock creates a wave. That wave is this like propagating, like self-propagating disturbance in the water. So it ripples out, and as it ripples out, the water lifts up. So water lifting up in the air is what we would call charge. Like if I magnetically charge something, or my battery has a charge or whatever like that, it's a movement of that charge is this, it's an arrangement or a disturbance between these three other charges: the ground, the medium, and the surface between that medium and some other more rarefied dimension. Just like sand, water, and air. Like if you're talking about any sort of wave, you're always looking at that. You have to have those three parts. You have to have this. You have to have the sand. You have to have the water, and you have to have the air. Otherwise, it's not possible to have a wave. Like the concept makes no sense. A wave. So when something's waving, there's this relationship changing between three things. And then those three things exist, and the wave doesn't really actually exist in the sense of it's not the matter, it's not the thing that you're looking at, it's going through the medium. Right? So we're studying waves, and it's like we can't see waves, so we have to look at what does a wave do when it goes through water. It's basically what I'm trying to say. So once you see what a wave does when it goes through water, we're not studying water, we're studying the waves. If something has a wave function, it's like we know we're studying three other things that we're like not really noticing, especially if we're focused in on the waves. And this is like a logic tree. This is like this is similar to a thought experiment or a thought proof, ensuring like the terms at all have any sensibility whatsoever. Like when people are speaking, like when I say, hey, give me an answer on this question, and some of you write words and it has meaning behind it, and some of you either don't understand the question or don't really want to put the effort into it, and it just writes like the words are like this empty shell of meaning. It's like a false answer. It's like where you just perform the answer that you want. Right? Like I'll ask like a deep contemplative question, and then it's just blah. And sometimes some kids will write like a half a page of just the shell of the answer. So when you use like a word like a wave, which is how electricity behaves, it's how electron orbitals behave, it's the reason behind like electron orbitals, which is the reason behind all the chemistry rules. It's the reason behind how atoms look the way they do, like what color they are. It's like, so this is the why. This is the why underneath all physics. Is you're looking at how does energy move through matter. And to recognize when you're looking at the matter in the medium or when you're looking at the waves in the medium, the movement. And so there's absolutely no set answer. Like I'm doing this with you guys at the same time, because like as you think, every time you think about something for real, which is what I'm asking you to do, I'm asking you to think about something for real. That's it, right? So it's a physics class. So I'm saying like, hey, try and think about and like learn what a wave is. So the first bridge to that is an analogy. So learn what a physical wave is, an ocean wave. That's the simplest thing. It's super complex. There's still more to be discovered, but it's like right there in the ocean. I have videos showing what happens as it goes through the water. We can all watch that. So you just diagram that. You just understand that. Like just understand and diagram an ocean wave. That's step one. Label it well. Show how it works well. Show that you understand what's happening. Like why is the energy rolling like that as the wave goes by? Let's say it's a tsunami that came from an underwater mountain. Why is the energy rolling like that? There was a landslide, and then why is it turned into this big rolling wave? This big like column of energy, right? So it's like, it's weird. This big column of energy is moving through the water, and it's a column made of rotating wheels all stacked on top of each other. And then those wheels rotate and roll through the water like non-physical wheels, like energetic wheels. And so that as it rolls, as it rotates through the water, it lifts up the water into the air. That's what makes it charge. And so the same thing happens with light. And then also in the magnetic field, right? So we're talking about magnets, we're talking about electricity, right? The standards just say like blah, blah, blah. Here's what a charge is, here's what a charge does. And it leaves all of this blank because most people have a very difficult time conceptualizing it. But it's not any more difficult to conceptualize than, say, doing a one-arm handstand or so. Like it's a specialty, right? So I'm teaching you how to use water to help you form concepts of that whole thing, because it's all about energy moving through energies. And so water, it's right there. Water is like throwing bubbles into the fan. I can suddenly see what the air is doing. Water is like putting smoke into the air zuka. I can suddenly see these ring vortexes, right? Like water is that, but to the electromagnetic field. So once you start to wrap your head around those terms, right? Like terms like medium, right? So when I say medium, when I say electromagnetic field, anytime I say a field or a medium, you're looking at something that's analogous to a body of water. And then when that medium has waves rolling through it or has currents in it, that medium is said to have a field strength. So what's the field strength of an electromagnet is the degree to which it has like distorted this medium. So it's just the opening part of the book. It goes up, positive magnetic field, negative magnetic field. They attract each other. Okay, why? Here we go. And it's not even, it's not in that traditional understanding of like studying the phenomenon. You just have to study the words that are already known about the phenomenon very clearly to understand it better. It's like, okay, the electron behaves like a wave. Okay, well, how do I learn that? I could read a ton of books on it. Okay, where are waves that I can study? Boom, water. So 50% of quote unquote quantum mechanics, or the highest level chemistry imaginable, molecular bonding theory, is understandable through 12 years of graduate studies, or go look at it directly, do the science yourself. And so we have with water. So as you map that wave, then I'm saying, okay, compare this to an electric wave. I'm showing you what happens as electricity moves through a wire. How does the magnetic field move? Okay, when I say magnetic field, what am I referencing? Ground, field, and then rarefied medium, right? So, okay, the magnetic field's twisting around a wire when current flows. Okay, the field is the water, is the current, right? So what's the wire? Is that the rarefied medium or is that the ground? The protons in the middle of atoms seems to be the ground, seems to be the sand, seems to be the beach. That the field, the medium, the electromagnetic field, the magnetism, like the field, that's what everyone draws when they draw the lines around a magnet or the lines of force around a wire to make an electromagnet. What they're drawing is the current, like the direction things want to go in that field. And so when that field vibrates or has, it has particular vibrations in it, the surface of it, we see that as light. If it vibrates at this frequency, it's green. If it vibrates at that frequency, it's red. If it vibrates at this frequency, it's a X-ray, gamma ray, right? And then if a bunch of those frequencies of vibrations, we see them all at the same time, you can see that as a bigger wave that looks like an electron or that looks like a water buffalo, right? And then a water buffalo is like one of these waves that we're looking at. It's a wave, and it's comprised of tiny little ripple waves, which we see as a light, right? Light is the tiny little wind waves. And then electrons and objects are like bigger, massive rolling columns of water. So there's this medium, it's like the electromagnetic medium, that's how charge flows, either from the power plant or in the plasma globe. Like, it's flowing through a medium. So what are we looking at? I'm saying, like, understand the wave. So literally for the rest of the quarter, we're just looking at this wave. It's right there. Some of you guys know how to surf it. Right? Some of you know how to actually literally ride this phenomenon that I'm talking about. So we're trying to intellectually crack open this thing that some of you have, like, I can hardly surf. I haven't had time to learn how to surf yet. So it sets up this weird situation to where with some of you, like, I'm teaching you about something that you know better than I do. And there's a lot of things out there in the world like that. And so this whole assignment and everything is we went through and we did the quizzes and we did the books and we've learned enough of the chapters for the year, and I think we're like ahead by like 50% versus the pacing that you guys would have been on with just the fact stuff. So we're like super far ahead, right? I just blew through it. Here's the words, here's the stuff. Come on, it's not hard, right? So now we have 3 weeks of I want you to do real science, real thought, study this real thing. There's no answer here because you know it better than I do sometimes. And it's at the frontiers of human comprehensibility. It might take you 8 years to learn the math, but you can surf today. In the same way, you might not understand the math behind molecular bonding orbitals yet, but you can understand the principles and the concepts right now. And so this is more of a training exercise than it is this traditional get the right answer dance. It's like we're thinking hard. I'm like saying, here's all these ideas brain, and it's like you don't understand it. You don't understand what I'm talking about. You don't understand the connections. Right? So to think that's where imagine a real scientist, right? You have to not be afraid of that area. They can learn everything. People can learn everything in the world. And then be afraid of this experience that you're having right now. and it's really interesting watching the reactions. Like some of like it's like throwing a bunch of kids in the ocean and seeing what they do. Some of them run back screaming to the beach saying like ah, and then a couple of you are out there like going deep, like real deep, right? And the temperament quality is the same. So like you're seeing it with response to this assignment, a lot about everybody's temperaments and everything else too, like your own, other people's, in terms of like your attitudinal response to the actual scientific process. And it's not even bad. It's not even bad. Like for those of you that aren't interested in this and like that's you, I fully support it. And so then there is some standards of like, here's the minimum that you have to do. Like just go out there, look at the wave come in. Yeah, whatever, Mr. Hardesty. But yeah, here, just do this to get the A, and that's cool. And then there's the like, whoa, like realizing that you are on par. Like I'm showing you your scientific instrument of making patterns, drawing connections, and relating things together in the actual unknown. Like it's like the science where you have the right answers of like, hey, this is the category, this is where the answer goes. That's just all vocab. It's all vocabulary. So the assignment is, as safely yet elusively as possible, do the science. Like, here's a wave, here's this underlying pattern to it. I'm going to keep saying it. I'm going to keep trying to teach it. It's infinitely comprehensible. You're never going to be done with this. So the assignment is to work on it for the length of time that you have to work on it and to make it as good as possible in that length of time. And if you do this thing of like, I just want to get it done as fast as possible, or blah, 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 it's like, okay, whatever. Like class is going to be boring to you. But like some of you are getting this and are pondering it and doing, and it's you're out there swimming in the material to just for the sake of your own comprehension. And I can totally put a metric on that, but also we both know where, like, right? So it's not confusing. It just actually requires you to be answering some of those questions. Like it's the same as swimming. Like when the assignment's not this deep, you can get out of or not actually be self-directed. But with this one, if you're not self-directed and you're not out there like actively swimming in the arena that I've set up, right? There's a concept arena that I've set up based on the pattern of water, based on a pattern that I've taught you about water. I've thrown all these ideas out there based on a pattern that we find in electricity, based on a pattern that we find in chemistry. So I've thrown all these ideas out there in front of you and I'm going, okay, like recreate this. Either copy what I did exactly or actually swim. See what I did exactly as an example and do it and really do it yourself. One of those two things. So the assignment, really understand a water wave. And then use that understanding of a wave in general to understand a wave of electricity or a wave of light or any other thing that you're talking about. Like in waves, there's wheels, there's vortexes, there's spirals. So a wheel is a wave. You can make that analogy. Like a wheel is a wave. So it's an easy project, but it's also like it's a pretty big deal if you like sit there but you have to just do it. But if you do it, you're in it, you're doing science. The same way that I could take us on a field trip to the ocean and say, hey, let's learn how to swim. And then there's all these different degrees of interaction in the swimming of like, oh, do you go in at all? Do you just go in the tide pool? Do you go up to your knees? Do you go all the way in? Do you go in deep enough to like figure out how to float? Do you go in deep enough to feel like waves crashing into you or going under you or whatever? It's the same thing with the mind, or with language, right? The scientific language. I try not to even teach you guys that much theory. I try and teach you like very verifiable, factual data points, and then throw them at you so that you have to sort them. That's why it seems like a lot of some of the frustration with my teaching style is justified because I'm new, but some of it is frustration that I'm trying to cause on purpose. Right? And if I'm having a good day, I'll be like, everything that I'm doing wrong is on purpose. To provide appropriate resistance to train the muscle or to train the strength that I'm trying to develop in you. So that's called making analogies.